Okay, well then, let me do a couple of problems and focus on the explanations, on what you should explain when you solve these problems. So I'll take those directly from the homework. So the first was about population of insects. The population of insects increases at the rate uh, 6t plus 0.3t squared insects per day. Find the insect population in 5 days. Assuming there are 50 insects at t equals 0. So what I'm going to explain is why is it that an integral can be used for this problem. So the concept of integral, the word integral, the symbol of integral, will show up at the very, very end of the solution. And as soon as it shows up, you practically finish your solution. Because as soon as you know what the integral is, you plug it into Wolfram alpha and get the number. That's the end of it. So you do not start with, oh, population is an integral and go on explaining how to compute it. You have to explain why you use the integral. And here's the explanation of why. The idea is that you have to keep track of insect population. So that's a numerical value that depends on time. So you introduce a function now. So let f of t be the insect population. And at this time you choose a parameter that you consider being useful for integration. So that's the first step toward the ultimate goal of setting up the integral. You choose the parameter. And the parameter is going to be time. So time, notation is going to be t. And what is going to be the interval where that parameter changes?
0 to 5.
From 0 to 5, we assume that we start at time t equals 0, and the question asks what happens in 5 days, so t changes from 0 to 5. Okay, now once you chose the parameter and once you know what the value you have of the ultimate interest, you have to somehow explain why that value can be expressed as an integral with respect to the time. And you begin with the simple case, linear case. When the situation is particularly simple, when your insect population can be written as a product right? Time, interval of time times what? Some rate. Right? So rate of change multiplied by time spent. But this equality holds only if the rate is constant. All right. Now, the difficulty we have is that the rate is not constant over that time between 0 and 5. And the way to adjust to that is to say that instead of this equality, we are going to subdivide our interval into short pieces. So we subdivide the interval from 0 to 5 into short pieces of length delta t. And then we argue that if we subdivide, then how do we relate the change of the population over the whole interval to the change over short interval?
Use geometric approximations.
So the total change of the population, the total change of the function, is equal to the sum of the total changes over those intervals. So this is the beginning of our build-up of the integral. And this is exact equality. Right? The total change is exactly equal to the sum of incremental changes over those intervals of length delta t. And then we would like to work on this sum. And what we say is that delta f over the ith interval is approximately, what is it approximately? Now we use that equality, but approximately. We say that the rate over that short interval, over ith interval, is not constant, but it's approximately constant. So the change of the population is approximately the rate over that interval times delta t. And now the rate is given, so let me denote it by something like r of t. So that is going to be r of some ti times delta t. So I approximated the incremental change, and now I use this approximation in the summation. So the total change of the population is again equal to the sum of those incremental changes, and that is approximately equal to rate over the ith interval times delta t. And we are now very close to the expression like an integral. Now we argue that we expect this approximation to become better as we make delta t go to 0, as we subdivide into shorter intervals. So this approximation becomes better and better approximation of that total change, and the total change is actually the limit as delta t goes to 0 of those sums. And now we say this is, by definition, a definite integral. And then we recognize what should be the integrand. It should be exactly that function r of t. We integrate with respect to t, and the interval is our original interval from 0 to 5. And the rest is easy. The rest is saying that now we just have to compute the integral from 0 to 5 of that function 6t plus 0.3t squared. And that is, antiderivative of this is 3t squared plus 0.1 t cubed, evaluated at 0 and 5. At the t equals 0, it's equal to 0. When t equals 5, it's 3 times 5 squared plus 0.1 times 5 cubed. So 75 plus 12.5, 87.5. And now I'm done with the problem.